Okay, so here's the first problem we're going to look at. 2 2/3 times 1 2/3. And the first thing I want you to do is I want you to take your pencil or pen or marker, whatever you're using, and put a little dot up in the corner, and that's going to be our starting point. Okay? Now, one of the things we should know is that if we have a multiplication problem, and I'll draw a small one down here, such as 2 times 3, okay, we know that that equals 6, and we can draw that as an array, 2 by 3, and so our answer there for that array is 6. So the answer to our multiplication problem is equal to the array. And instead of drawing dots, what we could draw is boxes. And so we could say that the area of this box, which is 2 by 3, is 6. So the answer to the area of a problem is the answer to the multiplication problem. Okay, so what we're going to do here is we're going to look at creating an area problem. Okay, so the first thing I want us to do is, starting at this dot, with each of these spaces equaling 1/3, I want you to draw a line that would equal 2 2/3. Please go ahead and do that now. Lots of different ways you may have chosen to do this. Here's how I've chosen to do it. If I know that each box is 1/3, I know that 3/3 makes one hole, and I have 2 holes. So 1 hole, 2 holes, and beyond that I need to go 2/3. So I went 1/3 more, 2/3 more, and there is my first line. Okay, same thing for 1 2/3. So instead of going across this time, we're going to go down. So starting at the dot, we're going to go down 1 2/3. Please do that now. Okay, so we have a line drawn out that is 2 2/3 going horizontally and 1 2/3 going vertically. And so in order to create the area of that problem, we're just going to have to go out and extend these lines until they connect. And it looks like they're going to connect right here. So if you want to draw a dot there so you know where to stop, please go ahead and do that now. Okay. Okay, so now if we could figure out the area of this shape, which is 2 2/3 by 1 2/3, then we would know the answer to our problem, what 2 2/3 times 1 2/3 is equal to. So let's go ahead and see if we can do that. So what I would like you to do is find out how many boxes are inside of here. Okay, and right now just count them as whole units and just say how many total boxes are inside of our rectangle. Please go ahead and count that and write your answer somewhere out here to the side. Okay, whatever strategy you used, you should have come up with the answer 40. I'm going to put 40 right here. And there's a lot of different strategies you could have used. One might have been to count all of the boxes, okay, and that would have given you 40. Some of you might again have realized that the answer to that multiplication problem is the area, so you could have said there are 5 boxes going down, and there are 8 boxes going across, and 5 times 8 is 40. So we know that there are 40 boxes inside of the rectangle. But one of the things we also know is we know that each of these boxes is not one hole, because they're not 1 by 1, they're 1/3 by 1/3. Okay, so we are going to have a numerator over a denominator, and that denominator is going to represent the size of each box. So, can you tell me the size that each box is equal to? Think about it for a moment. What is your answer? Okay, well, it may not be what you think. Some of you perhaps are answering, well, since each box is 1/3, then we have divided this into thirds. So it would be 40 over 3. Okay? Well, problem with that is the boxes are not 1/3. They are 1/3 by 1/3. Okay? So take a look. Here is our 1. Remember we said this was 1. We counted over to make 3/3, 1 whole. And we counted this way to make 3/3, 1 whole. So there are not 3 boxes to 1 whole. There are actually 9 boxes to 1 whole. So each box represents 1/9. Okay? So when we counted all of these out, we didn't get 40. We didn't get 40/3. We got 40 over 9. And that is the answer to our problem. So now let's take a look at that answer and let's see how we can connect that to an algorithm that would help us to solve this without having to draw this diagram out every single time. Okay? So one of the things we said to get our numerator, one of our strategies could be to multiply the number of whole boxes, which we said was 5 from here to here, times the number of boxes going this way, which we said was 8 from here to here. Okay, and 5 times 8 is what gave us our numerator. Okay, and one of the other things we said was to get our denominator, we recognized that this was not thirds, but it was thirds by thirds. Okay, and we multiplied 3 times 3 to get our denominator, and that was 9. Okay, so looking up at this problem, where do we see these numbers? Okay, well, one strategy that we can use to solve a multiplication of mixed numbers is to convert each of these numbers into improper fractions. So we're going to look at 2 and 2/3. Okay, 2 and 2/3 is equal to, there's 1, which is 3/3. There's 2, which is 3/3 more. And there's 2/3 left over that we have to add on top of that. And if we add all of those pieces together, 3 plus 3 is 6, plus 2 is 8. And we get 8 over 3. And that's exactly what we see right here. And then the other number that we have is 1 and 2/3 going down. So this is 1, 1, 2, 3/3. And 2/3 more. And that is equal to 5/3. And 5/3 is the number that we have right there. So in a multiplication problem, one of the ways that we can solve a multiplication problem of fractions, whether those fractions are mixed numbers, converted into improper fractions, or whether they're just fractions that are already proper fractions, we can multiply across to solve for the answer in a multiplication problem. I want to do one more example because in the previous example we had a same denominator, a common denominator. We multiplied 2 and 2/3 times 1 and 2/3. So 3 was our common denominator. How does it change things, or does it change things, if we have denominators that are not the same? So let's go ahead and do the same thing we did last time. Start with your dot here. I want you to go 3 1/3 out this way, and when you're going horizontally, each box will be equal to 1/3. And as we go down and do 1 3/4, we're going to change what each box means, because we don't have thirds here, we have fourths. So as we go down, each box is going to represent a fourth. So go ahead and draw your first horizontal line and your first vertical line where you think they should be. Do that now, please. Okay, so you can see what I've chosen to do is 1, 2, 3, that's 1. 1, 2, 3 is 2. 1, 2, 3 is 3. And 1/3, 3 and 1/3 will take me all the way out to here. And I'll stop right there. And then for 1 3/4, this time I had to count 4 to make my hole. 1, 2, 3, 4 makes a hole. And 3/4 more takes me to 1 3/4. So hopefully yours looks like that. If it doesn't, go ahead and correct it. And then again, we are going to look at where the 2 points meet to create our rectangle. Okay, so there we have our rectangle. And the next step that we're going to take, again, is just to look at the number of boxes, okay, that are inside of the rectangle. How many boxes do we find inside the rectangle? Go ahead and find a strategy to figure out the number of boxes in the rectangle and record that over here. Do that now. Okay, you may have chosen a different strategy than what I'm going to do, but what I chose to do was count how many boxes are going down. 1, 2, 3, 4, 5, 6, 7. So there are 7 boxes going in this direction. And there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 boxes that go in this direction. And 7 times 10, which is going to be the answer to our multiplication problem, is 70. Okay, but 70 what? That's the question that we need to answer next. We look at each box here and we said, well, these are less than a whole, okay, because the whole is right here. This is 1, because we said this was 4/4, okay, and that's equal to 1. And we said going this way that this is 1, because this is 3/3. So as we look down here, we see that this represents 1 whole. Okay? And so if we want to know our denominator, all we have to do is count the number of boxes inside of each hole. And that will represent what each individual box means, and we can come up with a denominator. Okay? Well, last time we had 3 by 3, and that was 9. This time we have 3 by 4, and that is equal to 12. So our answer should be 70 over 12. And again, let's look at where those numbers come from. Okay? If we're just going to go to an algorithmic solution, what those numbers mean, we can go back up here, 3 and 1/3, okay? 3 and 1/3 is equal to 3 over 3 plus 3 over 3, that's 2, plus 3 over 3, that's 3, and 1/3, or if we know the shortcut, 3 times the number of holes, that gives us 3/3 plus 3/3 plus 3/3, or 9/3, and we have one more, so that is 10/3. Okay, and remember, there's our 10 that we multiplied by. Okay, and for the bottom number, for the number going down, 1 3/4, 1 3/4 equals 1. This time we're dealing with fourths, not with thirds, so we have 4/4, and we have 1/3 more, for a total of 7/4. And that's where we get our other number, and we multiply 10 times 7. Okay, so if we're using a standard approach, we might say that 10/3 times 7/4. Well, that gives us 70 on the top. And thirds by fourths means that each individual box is a 12th of the whole. So each box represents 1/12. Okay, so now I'd like you to go ahead and try one on your own. So using this as your starting point, go 2 3/4 horizontally, and then go 3 1/2 vertically. I want you to draw your area, draw the rectangle, count the squares, determine the size of each individual square to determine your denominator, and then go ahead and write that out using a standard algorithmic form, improper fractions, to see if your answer is correct. Please go ahead and do that now. Okay, so here's my solution. You can see that I've counted the boxes, okay, and I got 11 by 7, so I put that up here. 7 by 11 is 77. That gives me my numerator, the number of boxes. And for my denominator, I got 4 by 2 because the boxes are 4 across and 2 down. So 4 by 2 makes each one equal to an eighth. I have 77/8, and that can be changed into a mixed number of 9 5/8. Okay, so looking at those problems and looking at what I've drawn here, I want to add to it a little bit, okay? Because one of the standards of mathematical practice is make sense of problems and persevering in solving them. So basically that just means, do we understand what we're doing, and different ways maybe that we could do that, okay? So one of the things I want to bring out here is the idea of number sense, okay? So if we've got a problem such as this, okay, what range of answers makes sense for our problem, okay? Well, one thing I know is I have 2 and a fraction, okay, and I have 3 and some fraction. So at a very minimum, if I multiplied 2 times 3, that would give me 6. And since I have a number plus a fraction and a number plus a fraction, I know that my answer has to be greater than 6. But another thing I know that is that 2 3/4 is less than 3. And 3 1/2 is less than 4. And 3 times 4 is equal to 12. Okay, so if I'm looking at this, here's my box that is 2 by 3. Okay, and I see that my answer, my area, is greater than 2 by 3. So my answer has to be greater than 6. But if I were to extend this out all the way to 3 going down, so 4 going down, 1, 2, 3, 4, which would be the next whole number, and take this out to the next whole number, which would be 3, okay, so there's 1, there's 2, 3 would put me over here, and if I were to look where that area meets, I would see that the area that is 3 by 4 is going to be larger than my answer. So one of the things that I need to know right away is that my answer should be between 6 and 12 in order for it to make sense. And as a matter of fact, I'm going to say that this area is probably larger than what's inside here, so it's probably even going to be bigger than 9, which is halfway between 6 and 12. Okay? And so let's begin by looking at that as well in a whole number sense. Okay? Because we said each of these boxes is 1/8. So here we have 1 set of 8, 2 sets of 8, 3 sets of 8, 4 sets of 8, 5 sets of 8, 6 sets of 8, 1, 2, 3, 4, 5, 6, 7, 8. There's another set of 8, so that makes 7 sets of 8. 1, 2, 3, 4, 5, 6, 7, 8. So I have to go down 2 more into the next row. So there's 8 sets of 8. 1, 2, 3, 4, 5, 6, 7, 8. So I go 1 more down into that row, and I get my 9th set of 8. And I have 1, 2, 3, 4, 5 eighths, not enough to make another whole. So my answer that I came up with by counting the squares is 9 wholes and 5 eighths left over, so 9 and 5 eighths, which is what I got when I changed that into a mixed number of 9 and 5 eighths.